Inside every nuclear power plant sits a reaction that, left alone, would spiral out of control. Engineers don't stop that reaction, they tame it. Here's how a nuclear reactor turns one of the most dangerous processes on Earth into steady, everyday electricity. It starts with uranium, specifically an isotope called uranium-235. Pack enough of it together and something strange happens. Its atoms become unstable enough that a single stray neutron can split one apart. When that atom splits, it releases a burst of energy and 2 or 3 more neutrons. Those neutrons go on to split more atoms, which release more neutrons, which split even more atoms after that. This is a chain reaction. Left completely unchecked, it multiplies exponentially, doubling and doubling again in a fraction of a second. That runaway version is what powers a nuclear weapon. A power plant needs the opposite. It needs that same reaction, but slowed down, spread out, and held at a steady, controllable pace for years at a time. The first tool for taming it is called a moderator. Fresh neutrons released by fission move too fast to reliably split new atoms. They simply fly past most of them. So reactors surround the fuel with a moderator, usually ordinary water, sometimes graphite. Neutrons collide with these lighter atoms and slow down. Slower neutrons are far more likely to be captured by the next uranium atom, keeping the chain reaction going at a usable pace instead of an explosive one. But a moderator alone can't fine-tune the reaction. That job belongs to control rods. These rods are made from materials like boron or cadmium, elements that are extremely good at absorbing neutrons without splitting themselves. Lower the rods deeper into the reactor core, and they soak up neutrons before those neutrons can cause more fission. The reaction slows down. Pull the rods out, and more neutrons survive to split more atoms. The reaction speeds up. Operators are constantly adjusting these rods, holding the entire chain reaction at a precise equilibrium, neither growing nor dying out. It's less like controlling a fire and more like balancing on a tightrope, one that has to hold steady for decades. All of this fission releases an enormous amount of heat, and that heat has nowhere good to go unless engineers manage it. That's the job of the coolant. In most reactors, it's the same water acting as the moderator, pumped continuously past the fuel rods to carry heat away. Without it, the fuel would melt through its own casing within minutes. This exact failure, coolant that stopped flowing, sits behind almost every major nuclear accident in history. Here's the part that might surprise you. After all of that, splitting atoms, chain reactions, tightrope walking control rods, a nuclear reactor's actual job is stunningly simple. It boils water. The heat carried away by the coolant is used to turn a separate loop of water into high-pressure steam. That steam rushes through a turbine, spinning it at incredible speed. The turbine turns a generator, and the generator produces electricity. Strip away the nuclear physics, and a nuclear power plant is, at its core, an extremely elaborate steam engine. One more layer keeps this entire system safe. The reactor core sits inside thick steel and concrete containment, designed to hold in radiation even if every other system inside fails. It's the last line of defense in a design built around one simple principle: multiple independent barriers, so that no single failure can ever be the only thing standing between the reaction and the outside world. A nuclear reactor is really just 5 systems working together. Fuel that wants to react, a moderator that lets it react at a survivable speed, control rods that fine-tune that speed by hand, coolant that carries away the heat, and a turbine that turns all of it into electricity. Remove any one piece, and the whole system either shuts down or becomes dangerous. Keep all 5 in balance, and you get something remarkable. One of the most tightly controlled processes on the planet, quietly running in the background of everyday life. The next time your lights turn on, there's a real chance that somewhere, a chain reaction is being held on a knife's edge to make it happen. What other technology in your life is that carefully controlled, and you never even think about it?